recording, we'll discuss gas transport. Okay, so in order for pulmonary and tissue gas exchange to happen, oxygen and carbon dioxide have to undergo chemical reactions that allows for these poorly soluble gases to be transported in the blood. Okay. So your body's kind of a genius. Only 1.5% of the oxygen that we have breathed in is dissolved in the blood plasma because oxygen does not have a high solubility within water, okay, in the plasma itself. It's poorly soluble. So instead, the majority of your oxygen is actually transported by hemoglobin within your red blood cells, okay, which you actually knew that already, right? Like you knew that, but now like you know why. Okay, so oxygen is poorly soluble, so it's not going to go through the plasma. Instead, it hitches a ride on hemoglobin molecules on red blood cells themselves. Carbon dioxide, on the other hand, is converted into a substance called bicarbonate. Okay. This is going to be transported a little differently. Okay, bicarbonate, you're going to hear bicarbonate a lot. Okay, because your ventilation and your carbon dioxide levels affect your acid-base homeostasis, and that's going to be a big old deal, okay, over the next couple of chapters. All right, so the oxygen, we said it's going to be bound to the hemoglobin, okay, which we abbreviate just HB. Okay, hemoglobin both binds and releases oxygen. Okay, we call it loading, and we call it unloading. We're going to load up the hemoglobin with oxygen, and then we're going to have to unload it. So during loading, okay, oxygen is going to bind to the 4 hemoglobin molecules within each red blood cell at the pulmonary capillaries. Okay. This converts hemoglobin from the deoxyhemoglobin stage. Okay, so deoxy without oxygen. Okay. We're going to turn it into oxyhemoglobin because we have put the oxygen on it. Okay. 98% of your oxygen is bound to hemoglobin for transport. The other piddly 2% is dissolved in your plasma. Okay. And then we have to unload it. Okay. Your hemoglobin at your systemic capillaries, so at your cells. We're going to unload the oxygen from the hemoglobin. We're going to dump it off into the cells and tissues. Okay, so we've turned the hemoglobin back into deoxyhemoglobin. Okay, that oxygen will then be used by the cells and the tissues, obviously. Okay, and then the oxygen poor blood just goes back to the lungs eventually, so we can do it all over again. Okay, so this is what it looks like. At the alveoli, we're going to put all the oxygen onto the hemoglobins. Okay, so each hemoglobin can hold 4 oxygens. Each red blood cell has tons and tons and tons of hemoglobins. Okay, we then transport that blood through your body. Okay, we drop off all that oxygen at the tissues so they can use it. Okay, and the oxygen poor blood goes back to the heart so we can get it back to the lungs. Okay. All right, so the percent of hemoglobin that has bound oxygen is called percent saturation. Okay, so hemoglobin actually has a strong affinity for binding oxygen. It really likes to load up on oxygen. Fully saturated hemoglobins would be 4 oxygens bound, 1 to each of the 4 heme groups. This would be considered 100% saturation or fully saturated. Anything less than the 4 heme groups being fully bound would be partially saturated, so you can have either 1, 2, or 3 oxygens bound, and therefore you could be 25, 50, or 75% saturated, okay, for 1 hemoglobin molecule. Okay, so you have probably had your percent saturation monitored at the doctor's office, okay, and it was hopefully much higher than 75%. So This is really just talking about like one hemoglobin, but since you've got millions and millions and millions, okay, and they're all kind of doing their own different thing at different times, we can achieve higher than a 75%, but not necessarily be exactly at 100% at the same time, okay? So that's where all those different numbers might come from at the doctor's office, okay? Hemoglobin saturation depends on two things. Oh, look, your favorite, partial pressure of oxygen in the lungs and the tissues, okay? As well as the affinity, or how tightly or how strongly bonded the oxygen is to the hemoglobin itself, okay? So we said hemoglobin has a pretty strong affinity for binding oxygen. It really likes to grab oxygen and hold on, okay? Higher blood partial pressures for oxygen favors a loading reaction. So the more oxygen that you have in your blood, the more we can load up the hemoglobins. Okay. If you have lower volumes of oxygen, okay, so lower partial pressures, if you have a little less oxygen than normal in your blood, this favors unloading. Okay. So we have fewer oxygen molecules that are available to bind to hemoglobin, but if your blood doesn't have a whole lot of oxygen to transport in the first place, your cells and tissues are probably getting kind of desperate for oxygen themselves, so we're actually going to favor unloading what's attached to the hemoglobins, and we're going to give it to the cells and the tissues so they can continue to live. Okay, so we can measure. Okay, we can measure the relationship between the partial pressure of oxygen and the percent saturation of hemoglobin molecules. We call this, are you ready? Oxygen hemoglobin dissociation curve. Fancy science. Okay, under resting conditions. Okay, only about 25% of your oxygen is actually bound to hemoglobin. Okay. The hemoglobin is going to be unloaded at the tissues. Okay. The remaining 75%, okay, we just keep a hold of it. Okay. So under resting conditions, only 25% of the bound oxygen is going to be unloaded at the tissues. Because if you're resting, you're not doing a whole lot. You don't need a whole lot of oxygen. Okay. You're not just cranking out carbon dioxide. You're just hanging on. But that leaves 75% for a reserve if we do have oxygen demand increases. So you were at rest, right? We're only normally unloading 25% because you're just kind of getting by, you're just living your life. And then suddenly you're like, I'm going to get on the treadmill. I'm going to exercise. You know that with exercise, you now have an increased demand for oxygen. Coincidentally, we have this nice oxygen reserve, this other 75%, that we can start unloading that during our exercise as well, while we continue to suck in oxygen, if you're me, because you're out of shape. It's okay. I'm not judging you. Okay. So, the affinity of oxygen by the hemoglobin molecules. We have three things that can actually change the affinity. And we do that by changing hemoglobin's shape, which is kind of cool. So we have three things that promote unloading, and we have three things that promote loading. And you will notice that they're basically the same three things. They're just going in opposite directions. So, factors that promote oxygen unloading, okay, which means we're going to take the oxygen from the hemoglobin, we're going to put it in the tissues. Okay, we're going to use the oxygen. Okay, so those three things are going to be increased carbon dioxide levels, decreased blood pH levels, or increased temperature levels. Okay. So, let's talk through these. Increasing CO2. So you got a lot of CO2. Do we like a lot of CO2 in our cells? No. How can we help combat that? We can do tissue gas exchange. Okay, we can get rid of that CO2 and we are going to switch it for oxygen. Okay, so we're going to take the oxygen off the hemoglobins. We're going to put it in the tissues. Okay. Decrease blood pH. All right, so our blood has gotten too acidic. We've dropped below 7.35. Okay? One of the ways that we could do that is by having too much carbon dioxide in our blood. Okay? So what do we do about it? Well, we just said, okay, for carbon dioxide, we're going to get rid of the CO2 and we're going to unload the oxygen into our tissues. Okay, this would raise our pH back up to the 7.35 to the 7.45. Increased temperature. Okay, the easiest way you can think about that is our exercise example. What happens when you exercise? You get hot. Okay, coincidentally, what also happens when you exercise? You are sucking in oxygen. Okay, because you are making CO2 like crazy. You could be affecting your blood pH. So what do? We get rid of the CO2. We keep our pH where we want it. How do we do that? All of that oxygen sitting on those little hemoglobin molecules, we unload them into the cells and tissues for use. Okay? Again, all of these three promote oxygen unloading. We're taking oxygen from the hemoglobin, we're putting it in the cells and tissues to use it. Okay? Now, we have three factors that promote oxygen loading, okay, which means the oxygen is going to stay bound to the hemoglobin molecules. They're really just the opposites. So up here we had increased CO2, down here we have decreased CO2. Now we have increased blood pH, now we have decreased body temperature. Okay, if you are really, really chilly, okay, like really chilly, like -2 outside, and you're shivering, okay, you really have no need for increased oxygen use. So you are going to keep most of the oxygen bound to the hemoglobins, and you're really only going to unload the oxygen at your vital organs, okay? If you do not have increased oxygen usage, okay, you're not really going to have extra CO2 floating around. Okay. We could decrease your CO2 levels. Perhaps you are, I don't know, hyperventilating. Okay, maybe you are hyperventilating. That would, that would drop your CO2 levels. Okay, this would also actually increase your pH levels. Okay, if you are going to do that, okay, if you don't have as much CO2 floating around, okay, or if your blood pH has gotten a little too high, okay, you're not going to want to use extra oxygen. It can just stay right there on the little hemoglobin molecules themselves. Okay, we can just use it later once everybody calms back down. Okay, once everything returns to normal. Okay, so these three, unloading, we're going to use the oxygen. These three, we're going to load it up. We're going to keep the oxygen bound to the hemoglobin. We're going to save it for later. Okay, and you can see that here. Temperature increase causes unloading. You're going to take the oxygen, put it in the tissues. Okay, increased acid concentrations, okay, or increased carbon dioxide concentrations. All of those are going to favor unloading. Okay, you can see how that shifts the curve. Okay, that's one thing we hadn't talked about, but all of these factors, okay, all of these are going to change what this curve looks like. Okay, so in this picture, unloading, we go from the dotted line. Okay, we have a right shift. That's what it's called. Everything's moving to the right. It almost looks like it's moving down, but it's technically moving to the right. See, look, it's moving to the right. Right shift and left shift. I didn't make that up. Okay. All of these would be the unloading. Okay, and then our other three are low CO2, our high pH, our low temperatures, things like that. That promotes loading. Okay, so we're going to save that oxygen, and this gets us a left shift.